Okay. Air at atmospheric pressure and 200 degrees Celsius flows over a flat plate with a velocity of 5 meters per second. The plate is 15 mm wide and is maintained at 120. Calculate the hydrodynamic boundary layer thickness, thermal boundary layer thickness, and the local heat transfer coefficient all at x equal to 0.5 meters from the leading edge. Assume flow is on one side. If it is given on both sides, then you have to, here there is no issue at all. Otherwise, you have to find the heat transfer rate twice of that particular value. So take these properties. You are given properties in the problem, so only take these properties. Don't take anything from the data book. Now that's a simple sketch. The plate temperature is low, fluid temperature is high. So what will happen to the fluid? The fluid will cool down. Okay? Fluid is at 200, plate is at 180. So heat will transfer from the fluid to the plate. So the plate will get heated, the fluid will get cooled down. Or the plate is maintained at 120, so the fluid leaving will be cooler than 200. Is that clear? Because it is leaving some heat, you will have the fluid going cooler. Anyway, let's find all these values. To find these values, what is the first check that you have to do? The Reynolds number. To know whether the flow is laminar or turbulent. So first thing always, when you have a flat plate problem, you have to check the Reynolds number. What is the Reynolds number? You have to check at 0.5 meters whether the Reynolds number is less than the critical or the greater than the critical. So let's find Rex, which is u infinity x by mu. We have not provided those mu values, or you can find mu by rho equal to mu, or you can use rho u infinity x by mu. Rho is 0.815, u infinity is 5, x is 0.5, mu is given to be 24.5 into 10 power minus 6, and the Reynolds number is going to be 80,163.26. It's going to be the Reynolds number. It's clearly less than 5 into 10 power 5. Okay. That's going to be a 0.8 into 10 power 5. Clearly less than 5 into 10 power 5. So the flow is laminar. When it is laminar, you can use the correlations on the front page. So delta Hx, you have a formula. You have a formula for delta Dx. And for local heat transfer coefficient, what do? You first find the Nusselt number. And from the Nusselt number, you find H is Nusselt number based on x into k divided by x. So from the formula for Nusselt number, you always rearrange and find what is Hx. Now let me write the correlations for delta Hx. Delta Hx is given by 5x Reynolds number to the minus 0.5. Delta Tx is delta Hx into Prandtl number to the minus 0.333, and the Nusselt number is 0.332. Reynolds number to the 0.5, Prandtl number to the 0.333. Remember, this correlation has to be used only when Prandtl number is between 0.6 and 50. Here the Prandtl number is 0.7, so you can use this particular correlation. Now all you have to do is just substitute values. 5 into 0.5 into 83,163 to the power of minus 0.5. This will give you delta Hx. It's a thickness, so its unit is meters. Let us find that first. 5 into 0.5 into 83,163.26 to the power of minus 0.5. This is going to be 8.669 into 10 power minus 3 meters. Roughly, you can measure it as 8.7. Okay, so that's the thickness of the hydrodynamic boundary layer. Now the thermal boundary layer thickness is the hydrodynamic thickness into Prandtl power minus 0.333. So you can use 8.7 into 10 power minus 3, that is delta Hx, into Prandtl number is 0.7 to the 0.333. So this will be 8.7 into 0.7 power 0.333, which is 7.725 into 10 power minus 3 meter, or 7.725. So here you see the hydrodynamic boundary layer is thicker, thermal boundary layer is thinner. This will be the case when Prandtl number is less than 1. So when the Prandtl number is less than 1, you will see hydrodynamic boundary layer like that and thermal boundary layer like this. This is for the case Prandtl number less than 1. Please note that. Now we can find the Nusselt number. Why do we find the Nusselt number? To find the local heat transfer coefficient. Nusselt number is 0.332 into Reynolds number to the 0.5, 83,163.26 to the 0.5 into Prandtl number to the 0.333, 0.7 over 0.333. So this will be 0.332 into 83,163.26 power 0.5 into 0.7 power 0.333. This is going to be 85.02. That's the Nusselt number, and you can plug it in here. 85.02 into the thermal conductivity is 0.0364 divided by x is 0.5. 6.19 watt per meter square. Those are the values. Let's see the answers. Delta. Okay, there's a small mistake here. I have written minus here, but on substitution I have not put a minus. So that's a small mistake that we did. And the thermal boundary layer thickness happens to be 9.763 mm. So it's the opposite way. The hydrodynamic boundary layer is thinner and the thermal boundary layer is thicker. This is true when Prandtl number is less than 1. Sorry for that. So here you see thermal boundary layer thicker, hydrodynamic boundary layer thinner. When Prandtl number is less than 1, it's 1. The other way, the thermal boundary layer will be thinner and the hydrodynamic boundary layer will be thicker. All the other answers are perfect.
Stop one.